bond energy and bond strength. Okay, bond energy and bond strength. The energy required to break a bond or the energy released when a bond is formed between two atoms is called bond energy. Okay, the energy required to break a bond the energy required to break a bond or the energy required or the energy released when a bond is formed. A bond is formed. A bond is formed between two atoms is called bond energy. It's called bond energy. Okay. Energy required to break a bond. Energy required to break a bond or the energy released when a bond is formed between two atoms is called bond energy. Okay. The energy required to break a bond or the energy released when a bond is formed between two atoms is called bond energy. Okay. The energy required to break a bond or the energy released when a bond is formed between two atoms is called bond energy. Okay? A plus B. A plus B. Arrow mark of AB plus energy. Plus energy. Or AB. A bond B plus energy. Energy. Arrow mark of A plus B. That is the energy required to break. The energy required to break. The energy required to break a bond or the energy released when a bond is formed between two atoms is called bond energy. The unit of bond energy. Unit of bond energy. The unit of bond energy is kilocalorie. Kilocalorie per mole. Kilocalorie per mole. Okay? Kilocalorie per mole. Kilocalorie per mole. Okay? Or kilojoule per mole. Okay? The unit of bond energy is kilocalorie per mole or kilojoule per mole. Higher will be the value of bond energy. Higher will be the value of bond energy. Okay? Bond energy. Higher will be the value of bond energy. Higher will be the value of bond energy. More stable will be the molecule. More stable will be the molecule. Okay, more stable will be the molecules. Okay, it is a additive property. It is additive properties. It is additive properties. Additive properties. It is additive properties. Okay, additive properties. Bond energy value gives an idea about bond strength. Heat of formation can also be calculated from the bond energy. And heat of formation, heat of formation, heat of formation can also be calculated, from bond energy from bond energy value. Okay. For diatomic molecules, the bond strength is measured in terms of bond dissociation energy. For for diatomic molecules, for diatomic molecules, for diatomic molecules, the bond strength for diatomic molecules, the bond strength is measured in terms of bond dissociation energy. Bond dissociation energy. Okay. Bond dissociation energy. Larger the bond dissociation energy, stronger will be the bond in molecules, and the bond energy indicates stability of the bond. More the bond energy, more stable is the bond. Hence, bond energy is a measure of strength of the bond. Okay. In case of polyatomic molecules containing more than one covalent bond, it is expressed as 2s. First is bond dissociation energy. Bond dissociation energy. Bond dissociation energy. And second is average bond energy. Average bond energy. Average bond energy. Okay. Average bond energy E. Average bond energy E. Okay. Average bond energy E. For polyatomic molecule, bond dissociation energy is the energy needed to break one mole or bond of a particular time. Average bond energy E is the average of the difference bond dissociation energy D of all the bonds present in the polyatomic molecules. Okay. Bond energy for polyatomic molecules such as ammonia, methane, water, it is the average of the heat of formation delta HF divided by the number of bonds. As an example, CH4 arrow marker CH3 plus hydrogen and delta H1 equal to 102 kilocalorie per mole. And after some time, CH3 arrow marker is also converted CH2 plus H, and delta H2 equal to 105 kilocalorie per mole. And after some time, CH2 arrow mark of CH plus hydrogen and delta H3 equal to 108 kilocalorie per mole. And after some time, this CH is also converted in C plus H, that means carbon plus hydrogen, and this is delta H4 condition is 83 kilocalorie per mole. That is kilocalorie per mole, and that is the CH4 arrow mark of C plus 4H. C plus 1, 2, 3, 4. 4H is that delta HF. Delta HF. Okay, delta HF. That means delta HF means the average of the heat of formation. The average of the heat of the formation. Delta HF is the average of the heat of formation. That is delta H1 plus delta H2 plus delta H3 plus delta H4. That is 102 plus 105 plus 108 plus 83. That is 398 kilocalorie per mole. Kilocalorie per mole. Okay, kilocalorie per mole. And carbon hydrogen bond energy and carbon hydrogen bond energy carbon hydrogen bond energy is delta HF by 4, that is 398 by 4, and that is 99.5 kilocalorie per mole. Okay, hence in average bond energy E for methane molecule is 99.5 kilocalorie per mole. Okay, 1/4 energy is required to break 1 mole of methane in atomic carbon and hydrogen. Okay, 1/4, that is 1/4 energy is required to break 1 mole of methane in atomic carbon and hydrogen, which is bond energy of carbon hydrogen bond. It is not necessary that the energy required to remove 1 hydrogen atom from methane molecule is same. This quantity is called bond strength. More energy will be required to remove first hydrogen from methane molecules. Bond energy represent average of 4 bond strength. Generally, the strength of a bond depends upon electronegativities of different atoms and position of atoms in the molecules, whereas bond energy is constant. For diatomic molecule, the value of D and E are the same, but the polyatomic molecules they differ. Okay, and average bond energy E. Next is average bond energy E. Average bond energy E. Average bond energy E. Average bond energy E. What is the average bond energy E? Average bond energy E equal to energy required to break a molecule in atomic fragment. Energy required to break a molecule. Energy required to break a molecule in atomic fragments. Energy required to break a molecule in atomic fragment upon number of bonds in molecule. Upon number of bonds in molecule. Number of bonds in molecules. Okay, equal to heat of formation upon number of bond in molecule. Number of bond in molecule. Okay, example, as bond energy for the polyatomic molecules such as ammonia, water, etc. is the average of the heat formation divided by the number of bonds. The three bonds dissociation energies for ammonia molecules 435.1 and 397.5 and 338.9 kilojoules per mole, and number of bond in ammonia molecule is 3. The average bond energy of ammonia bond is 390.5 kilojoules per mole. The energy for water is calculated as follows. Water H2O. Example H2O. Arrow mark of H plus OH. That is delta H1 equal to 117 kilocalorie per mole. Kilocalorie per mole. And OH, arrow mark of H plus O, that is delta H2 equal to 103 kilocalorie per mole. Kilocalorie per mole. Okay, kilocalorie per mole. And that is H2O. Arrow mark of 2H plus O. Arrow mark of 2H. 1H, 2H, O. 2H plus O. That is delta HF. Heat of formation equal to 220 because 3710.0 and carry 112 and 112, 220 kilocalorie per mole. Kilocalorie per mole. That is OH bond. OH bond energy. OH bond energy equal to 220 upon 2, that is 110 kilocalorie per mole. Okay. Bond energy for single and multiple bond you can show hydrogen bond. Hydrogen bond 103. Hydrogen fluorine bond 134. Hydrogen fluorine bond 102. Fluorine bond 37. And chlorine bond 58. Bromine bond 45. Oxygen bond 190. Nitrogen bond 226. And carbon bond 83. R is kilocalorie per mole. And carbon double bond carbon is 145 kilocalorie per mole. And carbon triple bond carbon is 192 kilocalorie per mole. Okay. And oxygen hydrogen bond energy is 98.5 kilocalorie per mole, and oxygen hydrogen bond energy is 110 kilocalorie per mole. Okay. And next is a factor influencing the bond energy. Factor affecting the bond energy. Factor influencing the bond energy. First point, overlapping of bonded orbitals. Overlapping of bonded orbitals. bonded orbitals. Okay, overlapping of bonded orbitals. Okay, factor influencing the bond energy. First is overlapping of bonded orbitals. Energy of axial overlapping is more than sidewise overlapping. Value bond of energy depends upon the value of existence of overlapping. Greater will be the value of existence of extent of overlapping, more will be bond energy. Bond energy of carbon-carbon, carbon double bond carbon and carbon triple bond carbon is 83, 145 and 192 kilocalorie per mole. Okay, carbon-carbon bond, carbon double bond carbon, carbon triple bond carbon is 83, 145 and 192 kilocalorie per mole, okay, respectively. In carbon triple bond carbon, there will be overlapping of three orbitals. There will be overlapping of three orbitals. In carbon double bond carbon, 2 in carbon double bond carbon, 2 in carbon single bond carbon, 1 okay, orbitals overlap. Second is size of atoms. Size of atoms. Okay. Bond energy will be more on the smaller the size of atoms. Bond energy is more. Bond energy will be more and smaller the size of atoms. The size of atoms. Okay. Is that the bond energy of hydrogen bond is 103 kilocalorie per mole. Kilocalorie per mole is the greater than bond energy chlorine bond. Okay, chlorine bond 58 kilocalorie per mole. Okay, and third point, types of bond. Okay, for similar diatomic molecules, the value of bond energy differs in single, double, and triple bond. Hence, bond energy depend upon the type of bond. As example, nitrogen bond 160 kilojoule per mole, and nitrogen double bond nitrogen is 418 kilojoule per mole, and nitrogen triple bond nitrogen is 946 kilojoule per mole. This is the bond energy. Okay. Fourth point is bond length. Fourth point is bond length. Smaller the bond length, more will be the value of bond energy. Smaller the bond length, smaller the bond length, smaller the bond length, more will be the value of bond energy. More will be the value of bond energy. Okay, the value of bond energy. Okay, and the next is electronegativity value. Fifth is electronegativity electronegativity, electronegativity value. More will be the electronegativity, more will be the electronegativity, more will be the electronegativity, more will be the electronegativity difference between bonded atoms, okay. More will be the value of bond energy, and more will be the value of bond energy, more will be the value of bond energy, okay. Electronegativity difference in hydrogen fluorine is larger than hydrogen fluorine. Consequently, the bond energy for hydrogen fluorine molecules 134 kilocalorie per mole is greater than the hydrogen fluorine 102 kilocalorie per mole. Nature of hybrid orbitals. 6. Nature of hybrid orbitals. Nature of hybrid orbitals. Okay, nature of hybrid orbitals. As p character increases, the bond energy decreases. As p character increases, then if p character increases, then bond energy decreases. Bond energy decreases. Okay. sp3 hybridization. sp3 and sp hybridization. Carbon bond carbon, carbon double bond carbon, and carbon triple bond carbon. Okay. Hybridization is sp3 hybridization, sp2 hybridization, sp hybridization, and percentage of p character. Percentage of p character is 75%. That is 66.7%. That is 50%. Then the bond energy in kilocalorie per mole is 83, 145, and 192. Next is important and the way of competition and as well as board exam. Okay. 7 point. Resonance. Those molecules in which phenomenon of resonance takes place, their bond energy value will be more in comparison of molecules without resonance. Due to resonance, bond length is shortest and hence the bond energy is increases. Okay. Those molecules in which phenomena of resonance takes place, their bond energy value will be more in comparison to molecules without resonance. Bond energy in resonance molecule is more as compared to bond energy in without resonance. Bond energy in without resonance molecule. Okay. Those molecules in which phenomenon of resonance takes place, their bond energy value will be more in comparison of molecule without resonance. Due to resonance, bond length is shortest Due to resonance, due to resonance, due to resonance, band length is shorted, and hence the band energy is increased, and hence band energy, hence band energy increase. Polarity in covalent band. Polarity